What is a CPU? The central processing unit is the brain of a computer system. The CPU performs most of the processing inside a computer system. It executes instructions from software, performs mathematical calculations, coordinates hardware components, and manages data flow. As the brain of the computer, the CPU constantly processes streams of instructions from both hardware and software. A modern CPU has several key physical characteristics. It's a silicon-based integrated circuit containing millions or billions of transistors. CPUs are typically square or rectangular in shape and generate heat during operation. CPUs are found in all types of computing devices, from smartphones and laptops to servers and supercomputers. The CPU is the fundamental component that makes all modern computing possible. Now that we understand what a CPU is, let's explore its components. A CPU consists of four main components that work together to process instructions and data. These components are the control unit, the arithmetic logic unit, registers, and cache memory. The control unit is the CPU's command center. It manages and coordinates all CPU operations. The control unit fetches instructions from memory, decodes them to determine what they're asking the CPU to do, and executes them by sending appropriate signals to other components. It essentially serves as the CPU's traffic controller, managing the precise timing and operation of all components. The arithmetic logic unit, or ALU, is the CPU's computational engine. It performs all mathematical and logical operations. For arithmetic, the ALU handles addition, subtraction, multiplication, and division. For logic, it performs operations like AND, OR, NOT, and comparisons. When the control unit sends an instruction like add 5 and 3, the ALU performs the calculation and returns the result. Registers are small, high-speed memory locations built directly into the CPU. They store data that the CPU is actively working with. Different types of registers serve different purposes. The accumulator stores calculation results, while the instruction register holds the current instruction being executed. The program counter keeps track of the next instruction's memory address, and general-purpose registers provide temporary storage for various data. Registers are crucial for CPU performance because they provide the fastest possible access to data, much faster than even cache memory. Cache memory is a small, high-speed memory that stores frequently accessed data from the main memory. Modern CPUs typically have three levels of cache. L1 cache is the smallest but fastest and sits closest to the processor core. L2 cache is larger but slightly slower, while L3 cache is the largest and often shared among multiple processor cores. The cache serves as a critical bridge between the high-speed CPU and the much slower main memory, significantly improving overall system performance. Now let's see how all these components work together to execute instructions. The process begins with the control unit fetching an instruction from memory, typically through the cache. The control unit then loads necessary data into registers and tells the ALU what operation to perform. The ALU receives data from registers, performs the required operation, and sends the result back to a register. This process repeats with remarkable speed for millions of instructions per second, allowing the CPU to execute complex programs through these coordinated component interactions. The CPU operates through a fundamental process called the Fetch-Decode-Execute Cycle. In the fetch stage, the CPU retrieves an instruction from memory using the address stored in the program counter. During the decode stage, the CPU interprets the instruction to determine what operation to perform and what data to use. In the execute stage, the CPU's arithmetic logic unit performs the actual operation, such as addition, comparison, or data movement. Finally, in the store stage, the CPU saves the result to a register or memory location and updates the program counter to the next instruction. This cycle then repeats for the next instruction, forming a continuous process. What makes modern CPUs so powerful is the incredible speed at which they perform this cycle. Today's processors can complete billions of these cycles every second. CPU clock speed is the fundamental rhythm that drives all processing in your computer. Clock speed is measured in gigahertz or gigahertz. A processor running at 1 gigahertz completes 1 billion cycles every second. The CPU clock functions like a metronome, creating a steady beat that synchronizes all operations within the processor. With each tick of the clock, the CPU can execute an instruction or part of an instruction. A modern CPU processes instructions in a pipeline, with each stage synchronized to the clock signal. Each clock cycle allows the CPU to move instructions through the execution pipeline. Higher clock speeds generally mean faster processing. A 3 gigahertz processor performs 3 billion cycles every second. 3 gigahertz means 3 billion clock cycles in a single second. This incredible speed enables the CPU to execute billions of instructions every second. While clock speed is important, it's not the only factor in CPU performance. Two CPUs with the same clock speed can perform very differently depending on their architecture, number of cores, cache size, and pipeline efficiency. In modern CPUs, billions of transistors work in sync with the clock, enabling the complex digital processing that powers our computing experience. CPU clock speed remains a fundamental aspect of processor performance, determining the maximum number of operations that can be performed each second. Instruction sets are the fundamental languages that CPUs understand. An instruction set is like a dictionary that defines all the commands a CPU can understand and execute. These instructions are the basic operations that the CPU can perform directly at the hardware level. These include basic operations like addition, moving data between registers, comparing values, and controlling program flow. There are several instruction set architectures in use today, but two of the most common are x86 and ARM. x86, used by Intel and AMD, is a complex instruction set computing architecture, while ARM is a reduced instruction set computing architecture. ARM processors are generally more power efficient, which is why they dominate mobile devices and are increasingly used in laptops like Apple Silicon. x86 instructions can vary in length, while ARM instructions have a fixed length, making them easier to decode. Let's examine how a simple operation looks in different instruction sets. Consider a basic high-level code example in C, adding two numbers and storing the result. In x86 assembly language, this would be translated into a sequence of operations using registers like EAX and EBX. The same operation in ARM assembly would look different, using registers like R0 and R1 with a more straightforward syntax. Ultimately, both get translated into binary machine code that the CPU can directly execute. This binary representation is different for each instruction set architecture. Different instruction sets have significant implications for software development. Software written in high-level languages must be compiled or translated into the specific instruction set of the target CPU. This means the same source code needs to be compiled separately for x86 and ARM processors. Software must be compiled specifically for each instruction set architecture it will run on. Some applications are distributed as universal binaries, containing code for multiple architectures. Emulation can allow software compiled for one architecture to run on another, but with a performance penalty. Multi-core processing represents one of the most significant advances in CPU design, allowing processors to handle multiple tasks simultaneously. Instead of having just one processing unit, modern CPUs contain multiple cores on a single chip. This is essentially like having several CPUs in one physical package. Each core can process instructions independently, dramatically increasing performance. To understand the benefit, consider a system with multiple tasks that need processing. A single-core processor must handle each task sequentially, one after another. A multi-core processor, however, can distribute these tasks across its cores, processing them simultaneously. Think of multi-core processing like a team of workers. A single worker can only handle one task at a time, while a team can work on multiple tasks simultaneously. With 4 workers, they can complete 4 tasks in the same time it would take one worker to complete a single task. While multi-core processors offer tremendous potential, software must be specifically written to take advantage of multiple cores. Traditional single-threaded code runs on just one core, regardless of how many cores are available. Software developers must use parallel programming techniques to distribute work across all available cores. For optimal multi-core performance, applications must be multi-threaded. However, not all tasks can be effectively parallelized, and the operating system plays a crucial role in distributing processes across available cores. CPU cache memory serves as a high-speed buffer between the processor and main memory. It significantly reduces data access times by storing frequently used data closer to the CPU. Cache memory is organized in a hierarchy of levels, L1, L2, and L3, with each level providing different capacity and speed trade-offs. Let's examine the specifications of each cache level. L1 cache is the smallest but fastest, typically between 32 to 64 kilobytes with access times of about 1 nanosecond. L2 cache is larger but slightly slower, while L3 cache provides even more capacity but with increased latency. Main memory is vastly larger but much slower to access. To understand cache hierarchy, imagine a chef's workstation. The ingredients at immediate reach, like the L1 cache, are small in quantity but instantly accessible. Items on a nearby shelf, like the L2 cache, take slightly longer to reach but offer more storage. The pantry, representing L3 cache, holds even more items but requires more time to access. Finally, the storage room, like main memory, holds everything but takes considerable time to retrieve items from. When the CPU requests data, it first checks if the data is in cache. A cache hit occurs when the requested data is found in the cache, resulting in fast access. A cache miss occurs when the data isn't in the cache, forcing the system to retrieve it from slower main memory. Modern CPUs use sophisticated prefetching algorithms to predict what data will be needed next. By loading this data into cache preemptively, the system can often avoid cache misses, significantly improving performance. To summarize, CPU cache memory forms a critical high-speed buffer between the processor and main memory. The hierarchy of L1, L2, and L3 caches provides different balances of speed and capacity. Cache hits keep the system running efficiently, while cache misses cause performance delays. Modern CPUs use prefetching to minimize these delays by predicting what data will be needed. Modern CPUs generate significant heat during operation due to electrical resistance in their transistors. As electrical current flows through billions of tiny transistors, energy is lost as heat through a process known as joule heating. Several factors affect how much heat a CPU generates, including clock speed, voltage, the number of transistors, and workload intensity. As workload increases, more transistors become active, increasing power consumption and heat output. Thermal throttling is a crucial protection mechanism that prevents CPUs from overheating. When a CPU operates normally, it runs at its rated clock speed while maintaining a safe temperature. As workload increases, the CPU consumes more power and generates more heat. When the CPU reaches its thermal limit, it activates thermal throttling. This reduces the clock speed to lower heat production. While thermal throttling protects the CPU from damage, it results in reduced performance until temperatures return to safe levels. Various cooling solutions have been developed to manage CPU heat, each with different performance characteristics. The simplest is passive cooling, using a heat sink with metal fins to dissipate heat through increased surface area. While inexpensive and silent, passive cooling is only suitable for low-power CPUs. Active air cooling adds a fan to force air through the heat sink, significantly improving heat dissipation. For high-performance computing, liquid cooling offers the best thermal performance by using liquid to transfer heat from the CPU to a radiator. Liquid cooling systems circulate coolant to transfer heat away from the CPU to a radiator where it's dissipated into the surrounding air. Modern CPUs use dynamic frequency scaling technologies like turbo boost to optimize performance while managing heat. At idle or low workloads, most CPU cores operate at their base frequency, generating minimal heat. When demanding tasks are encountered, turbo boost temporarily increases clock speeds to provide extra performance. This frequency boost depends on several factors, including the number of active cores, current temperature, power delivery capabilities, and workload duration. The CPU constantly monitors temperature to ensure it stays within safe limits. As heat builds up, it gradually reduces frequency to maintain thermal equilibrium. Through dynamic frequency scaling, modern CPUs intelligently balance performance needs with thermal constraints, delivering maximum performance without overheating. The computing industry is at a fascinating crossroads as traditional CPU technology approaches its physical limits. Moore's law, which predicted transistor counts would double every 2 years, is slowing down as we reach atomic scales. Quantum tunneling, heat dissipation, and manufacturing challenges create barriers for traditional silicon technology. These limitations are driving innovation in new CPU architectures and materials. Quantum computing leverages quantum bits or qubits that exist in multiple states simultaneously, promising exponential speedups for specific problems like cryptography and molecular simulation. Neuromorphic computing takes inspiration from the human brain, creating chips that mimic neural structures. These can process information more efficiently and are ideal for pattern recognition and sensory processing. Specialized AI processors are custom designed for machine learning workloads, delivering dramatic performance and efficiency improvements for neural network operations compared to general-purpose CPUs. Recent advancements like Apple's M-series chips demonstrate the power of integration, combining CPU cores, GPU, neural processing units, and unified memory on a single chip. This approach delivers dramatic performance and efficiency improvements. System-on-chip designs deliver higher performance, lower power consumption, reduced physical size, and can be optimized for specific workloads. This integration trend will continue as computing needs evolve. As we look to the future, CPU technology will continue to evolve along multiple paths. In the present, we see enhanced traditional CPUs and system-on-chip designs pushing current technology to its limits. The near future will bring increasingly specialized and hybrid architectures optimized for specific computing tasks. In the longer term, quantum computing and entirely new computing paradigms may revolutionize how we process information. As our computational demands continue to grow, CPU technology will adapt through specialization, new materials, and novel architectures to meet these challenges, ensuring the continued advancement of computing capabilities.